kind of sucks that I can't draw pictures. I'm going to have to draw pictures with my finger. So yeah, the rectangle last time, but now your function is a linear function, so it's going to make a small box like this, which is a trapezoid. Sorry if I mispronounced that, but something like that, right? And the area of that, one way to see it is to take two such figures and then take one of them and sort of invert it like that, and then invert it like that, so you have two pieces fitting together, you know, so one of them is like that and the other is like that. Okay, so you line them up perfectly, it makes a big rectangle, and each side of that rectangle is the small side plus the big side, right? So the area of one piece is half of that, so it's 1/2 times f of a plus f of a plus h. Right? So that's times h. So I was looking for that formula, all right? So that's the geometrical interpretation. The analytical interpretation is, remember when I had k times b squared minus a squared over 2. You have to remember that k times a is f of a and k times b is f of a plus h. So that's equal to k. I won't go through such derivations all the time when they're not strictly necessary, but might help clarify it for you this time around. So you have this thing, and then the k gets absorbed into that, because k times x is our function, right? And so you get f of a plus h plus f of a times b minus a over 2, which is just h. Right, so we arrive at the same thing. That's good. What's the take-home message? The takeaway message, sorry. What's the takeaway from this? Well, in our picture here, we can just, instead of doing it like that, we can simply f of a plus double I plus 1 times h Right, so on each of these intervals, you get, you basically look at both sides and you make an average. Still don't get the answer we were looking for. Let's add a third thing. So the difference, right? So this minus integral let's take the diff and multiply it by a big number. All right. Doesn't get okay, so one thing that we've achieved is that we can reduce the number of steps and still get a good agreement. So with only 10 steps we get a okay agreement. So what's the general idea here? Well, you can apply this principle of just finding the exact integration for a simpler function, and then just making the interval really small so that the function looks a bit like the simple function you have. That's one way of doing it. All right, that's one way. But why should it even work? If you've ever heard about something called the Taylor expansion of a function, or just the expansion of a function, is you have a function f of x, and you write it as a series of approximations. So x minus a times the derivative at a plus x minus a squared times the second derivative at a over 2, etc., etc. So sometimes in very few circumstances, if you're dealing with just any old functions, but if you're dealing with physical problems, it's pretty often that you can approximate very well a given function by just a series of progressively more terms in this series, in this expansion, where the first term is a constant, the second term is a linear function, the third term is quadratic, the fourth term is degree 3, etc. So it's any time that you stop, you end up with a polynomial which approximates your function when you're close to the point around which you expand. So at a, this approximation is exact because x minus a is 0, so it's just f of a. And then as you get farther from a, more and more of these terms need to contribute to sort of correct for the fact that the function is not a constant, it's not linear, it's not quadratic. But as long as you stay relatively close to a, it's fine in most cases. And so the idea is that whenever you stop, however many terms you stop, all the other terms depend on the distance from a to a certain power. So if you stop here, all of the terms depend on the distance between x and a, at least to the power of a square. If you stop after this term, it's going to be to the power of a cube. And then when you make the interval small, you're making the distance between x and a small. So the error in your calculation, the terms you're not accounting for, when you make this x minus a go to 0, it goes to 0 pretty fast. So if it's to the third power, it's going to go to 0 faster than if it's to the second power. If it's to the first power, it's not going to go to 0 very fast. So you're going to have to make a pretty small interval to make it work. But as you take into account more and more terms, the convergence of your algorithm to the true answer is faster and faster. So you don't have to reduce the interval quite as much. And then the basic idea is that, okay, any function